Welcome to the Scientific Sense podcast, where we explore emerging ideas from science, policy, economics, and technology. My name is Gil Eapen. We talk with world's leading academics and experts about their recent research or general areas of topical interest. Scientific Sense is an unstructured conversation with no agenda or preparation. We cover a wide variety of domains where new discoveries are made and new technologies are developed on a daily basis. We are most interested in how new ideas affect society and help educate the world how to pursue a rewarding and enjoyable life rooted in science, logic, and information. We seek knowledge without boundaries or constraints and provide unedited content of conversations with researchers and leaders who love what they do. A companion blog to this podcast can be found at scientificsense.com, and this podcast is available on over a dozen platforms and directly at scientificsense.net. If you have suggestions for topics, guests, and other ideas, please send them to info@scientificsense.com, and I can be reached at gil@eapen.info. My guest today is Professor Randall McEntaffer, who is a professor of astronomy and astrophysics at the Pennsylvania State University. He specializes in the design, fabrication, testing, and implementation of X-ray diffraction gratings for high-throughput, high-resolving power astrophysical observations. Welcome, Randy.
Thank you.
Yeah, thanks for doing this. So I want to start with one of your papers entitled Water Recovery X-ray Rocket Grating Spectrometer. You say that the Water Recovery X-ray Rocket, WRXR, was a suborbital rocket payload that was launched and recovered in April 2018. The WRXR flew two technologies being developed for future large X-ray missions: X-ray reflection gratings and a hybrid CMOS detector. Before we get into the details, Randy, what exactly is a water recovery X-ray rocket?
That's a good question. And so we have a lot of NASA suborbital rocket programs over the years, and it's a great platform to be able to do low-cost access to space, both for scientific research and for technology development. Yes. And as you know, these rockets are launched all over the world in different environments, from the tundra to the desert, and often these rockets are not recovered, but for astronomical missions they almost exclusively are. And so our launch sites have been kind of limited, and our typical launch site is either White Sands Missile Range in New Mexico or Poker Flats up in Alaska. And because they offer an easy way of recovering the payload. Now, as astronomers, the targets that we see in the sky is dependent on our latitude. We can only see the sky above us, not the sky that's on the other side of the Earth. And so if we're able to go to southern latitudes, we can realize new targets for scientific study. And so getting farther down in latitude is always a goal. And there happens to be a launch site at Kwajalein Atoll, which is out in the Marshall Islands of the Pacific. Yeah. And the island that we launch off of is roughly 2 miles by 4 miles in size. And so being able to put the rocket back down on that piece of land is nigh impossible. And so launching into the Pacific Ocean requires that we recover the rocket from the ocean. And so this was the first astronomical payload that was recovered from the water. And so hence we named it the Water Recovery X-ray rocket.
I see. So these are small rockets. They go up and come down?
Right. They are large as rockets go in terms of solid fuel booster rockets. And so these The rocket, it's a two-stage rocket that utilizes a Terrier Mark 70 as the first stage, which is actually a naval surplus cruise missile. And then the second stage is the Black Brant, which is produced by a Canadian company. And those are one-offs that we buy from them, or NASA buys from them. And then on top of that is our scientific payload, and then a NASA payload, which is support equipment for our science. And from tip to tail, these usually, or at least our rockets usually, measure about 70 feet in length. And so they're about as tall as a 7-story building.
Oh, wow.
So they're not teeny tiny, but they're not as large as, say a SpaceX launch or an old shuttle launch or something like that.
Right.
But you're right. They just go up and they come back down again in a parabolic trajectory.
Okay. And why are they called X-ray rocket?
Oh, so we specialize in the X-ray regime of the electromagnetic spectrum. And so our photons, our light, so to speak, is much more energetic than, optical light that our eyes see. And so we want to see these energetic phenomena in the universe. We concentrate these rockets on taking a look at supernova remnants, or the explosions of massive stars, which give off a lot of X-ray emission in their interactions with their galactic surroundings.
So the payload, are they launched outside the rocket, or it stays in the rocket and comes down? So how much time do you get up there?
So we don't get a whole lot of time. The X-rays are easily absorbed by our atmosphere, and so we have to get to high enough altitudes where that doesn't occur. And so our cutoff for space is typically 150 kilometers. And so from above 150 kilometers, we have usually a total of 5 to 6 minutes is all. Wow. And so it's a very short amount of time to do our science. The entire launch from takeoff to landing is about 15 minutes. And then about a third of that is in observable space.
And so are these X-ray, so are you taking pictures in the X-ray spectrum, or what exactly is in the payload?
Yeah, and so spectrographs are typically, the ones that we make are non-imaging spectrographs, and such that we get no spatial information on the objects we're looking at. We just collect all of its light and then disperse it into what we like to call the X-ray rainbow, into the spectrum. And that gives us the physics of what's going on in those objects. And so we're spectroscopists. We really cared about the spectrum more than the image. Okay,
so you're after the composition of stuff, right?
Yeah, exactly. And so when we get that spectrum, if we get that spectrum, it can tell us information such as the temperature of the plasma that made the X-rays, the density of that plasma, what is it made out of, the energy that is required to make that plasma. And so there's a lot of information you can get about the physical characteristics of the gas that's emitting those X-rays, but also physical characteristics about, in our case, the explosion that created that supernova.
So in the 2018 launch, was there a specific objective, what you were looking for?
Yes. So for 2018, that launch was actually more of a technology development launch. And so it not only tested, as you mentioned, it tested these diffraction gratings that we make, as well as this hybrid CMOS technology. But a major thrust of this was also to test out this water recovery technology, because future rockets can now use water recovery and be utilized over more of the globe by doing so. And so that was a big step to be able to say, okay, we can do water recovery now, which gives us another technology that's been tested. And so the science that we wanted to do is to get a spectrum of the Vela supernova remnant. And unfortunately, due to a mishap during launch, our detectors were actually rendered insensitive to the spectrum that we wanted to capture. And so our data was lost.
Hmm. I don't know anything about the mechanics, Randy, but when it comes down, does the payload get detached from the rocket, or is it still in the body of the rocket?
Right, that's a good question. And so the first stage, that Terrier Mark 70, that only burns for about 6 seconds. And then after that time, it mechanically detaches from the second stage. Then the second stage goes off, and that takes us up into space. And then when we're up there, we detach from that second stage as well. So the only two things that are currently operating are our scientific payload and the NASA support equipment. And so at the very, at the juncture where that second stage met our payload, there's something that's called the shutter door that opens up and exposes our payload to space and allows us to do our observation. And so for 5 to 6 minutes, we steer onto target. We're held on target by an attitude control system. And then as we start getting down towards the atmosphere again, we close our shutter door back up, and then we re-enter the atmosphere. And so at this time, your first stage has already landed on its parabolic trajectory. The second stage is following a somewhat similar to one to the payload. And then the payload comes back down, enters the atmosphere, shoots out a parachute, and then comes down to the ground, hopefully easily.
So for 15 minutes, I would imagine you can fairly precisely determine where it's going to be in the water, right?
It's not too bad. So we have these circles we draw around the bullseye, so to speak, which are called our dispersion radii. And this gives us, our guesses at where it could be. But those guesses are based off of variable things like wind. And so as this rocket goes through the atmosphere twice, it can be influenced a lot in terms of, its original trajectory prediction can be changed quite a bit during its flight. And so the accuracy isn't as good as you might think. It's probably hundreds of square miles.
Okay, hundreds of square miles. Okay, so that's quite a bit of an area. And so one of the interesting instruments here is the X-ray reflection gratings. You have another paper, performance testing of a large format X-ray reflection grating prototype for the suborbital rocket payload. So I know that you do a lot of work in this area. So what is specific about this large format X-ray reflection grating?
Yeah, and so X-rays, as I mentioned earlier, have a lot more energy than, say, the optical photons that our eye detects. And part of that means that those photons have a very short wavelength. And so if you want to interact with light, you have to use structures that are about the size of the wavelength of that light. And since X-rays have very small wavelengths, you have to create very small structures. And so diffraction gratings use periodic structure to take light and disperse it into the spectrum. And so for us to take the X-rays from the objects that we want to observe and get the spectrum, we have to have those X-rays interact with very, very small structures and do so on a very large area so that we can do efficient observation during the small frames of time that we're given. So we want a lot of area to be able to collect a lot of light, but then we have to, on that very large area, make very, very small features. And so just to give you an idea, the features that we make are around 100 nanometers in scale, where a nanometer is 10 to the minus 9th meters. And so these things are, hundreds of times smaller than the width of a human hair. And so they're very, very small features that we're making on here. And so to do so, we use what's called nanofabrication.
So when the payload is up there, Randy, are you collecting raw data, or are you doing some processing as well?
Both. And so we collect raw data. Our detectors absorb the photons, turn that into a signal. and that signal is then stored on board, but it's also sent to a telemetry section and then telemetered or radioed back down to the ground. And so we have real-time radio dish tracking of the payload so that we can actually see the data real time, but then we save it on board as well. So yes, it is all raw in the sense that we are detecting those photons, turning them into charge, and then taking and processing that signal. But then there's some processing has to be done to, turning from analog to digital and whatnot to deal with the data.
And you mentioned, again, the 2018 mission, it didn't quite succeed, but you had a specific target, the Vela supernova remnant. So do you have enough maneuverability up there to actually look in a specific direction?
Yeah, the maneuverability is one of the NASA components, and that's the attitude control system. And they do a very, very good job. And so initially when we launch, there's a set of gyroscopes on board that have an idea of have a pretty good idea of our orientation. And so when the shutter door opens and we slew to our target field, the gyroscopes have an initial solution that gets us pretty close to that target field within a degree. And then there's a star tracker camera that images the sky, and based off of the pattern of stars that it sees, it can tell you exactly where it is in space within about an arc second, which is 1/3600th of a degree. And then it uses 3-axis jets to stabilize on that position and hold it to within less than an arc second. And so it's a very precise pointing, in fact.
Right, yeah. And so the reason we cannot do this from the ground is that we cannot get the X-rays to get to the surface.
That's
right?
Correct. Yeah.
And so is this the sort of technology, so from a cost perspective, where does this sit? Obviously, if you launch something that is more long-term, it's going to be more expensive, but you have more time. This is less expensive, I would imagine, per launch basis, but then you have only 6 minutes up there. So what is sort of the cost utility curve here? I don't know.
That's a great question. And so there's two major facets to this. First of all, it's just the pure numbers. And so if you take a look at a suborbital rocket, it costs a few $1 million to launch these things. And so it's maybe a $2 to $4 million program at a university to build it, and it's maybe the same type of money at NASA to support it and buy the rockets, etc. So you're looking at, call it $5 million to do something like this, and you're getting just a few minutes of data. Now, if you go up to orbital payloads, we should keep in mind that rocket payloads are quite large. And so you can't do the same science on, say, a CubeSat. And so CubeSats are very small, and you can't have large instrumentation like you can on a suborbital rocket. And so CubeSats have their place, and they're very useful, but they're a different category. If you want to talk about a equivalent type of telescope, you'd have to go to the next level, which is like a NASA Explorer mission. And those start off at, $150 million or $250 million if it's a mid-size one. And so there you make a payload for 2 years of use. It usually lasts longer than that, but that's the baseline. And so you rapidly go to much more expensive payloads. But then you say, okay, it's not 5 minutes, though, you get 2 years. And so then we have to take a look at, the other facet, which is the technology development. And so if you want to put hundreds of millions of dollars into a NASA mission or some of their large missions, which take billions of dollars, to reduce cost and to reduce risk of those missions, you need to have smaller missions doing the development to show that, hey, yes, this technology will work. And so that's really where suborbital rockets are invaluable, because they provide that platform while also doing science where you can test these technologies out and say, okay, we know how to build this for a space flight now. It's going to completely reduce the cost and risk associated with these missions moving forward.
Yeah, that's very interesting. So the real trade-off here is the size of the payload. There are technologies that can take smaller payloads at much cheaper cost, but that's not going to be sufficient. So if I understand this correctly, Randy, the experiments and the testing that you do in the suborbital missions are on payloads that are comparable in size to what you would deploy in an orbital mission?
That's right. That's right. So there happen to be more, there's a larger frequency of what are called small sats coming up in the near future. And so NASA has realized a niche that hasn't really been exploited, but can still produce good science. And these are orbital missions that are kind of on the order of this, on the size of a rocket, but then go into orbit. And these are typically called small sats. And they fly on things that are called like an ESPA ring, which is interface platform for larger orbital missions. And you can strap instrumentation onto these ESPA rings and create a nice satellite doing so. And so we're kind of in the early stages of investigating how much scientific use we can get out of these smaller sats. But I think it's an area that we're going to grow a lot into, because that will, in my opinion, be kind of the most bang for your buck, so to speak, in terms of orbital platforms.
Yeah. And this is a true, if I understand this correctly, true material science problem, as well as sort of a mathematical optimization problem, right? The design of these gratings.
Oh, for the gratings, for sure. Yeah. And so when we pattern all these really small features, we use a electron beam lithography tool. And so what that means is that we use a beam of electrons to sculpt out the lines that we want to draw. And so this beam of electrons is, only 10-ish nanometers in size. And then we expose an electron resist, as it's called, and that resist holds the pattern that you write into it. And it's almost like using photographic film. When photons expose photographic film and then you develop that film, you see the areas that are exposed versus the ones that aren't. When we make our gratings, we expose a resist instead of a film to electrons. And then when we develop it, the development tells us where the electrons have impacted the resist and where it hasn't. And so we can create patterns within this resist and then transfer those patterns down into the substrate that's holding it. And so we usually use a silicon wafer and then etch down into that silicon wafer in various ways. And so we most of our studies are how to manipulate that electron beam to make the perfect pattern that you want. And then B, how do you transfer that pattern in different ways to affect the topology of the features that you're putting on this substrate. And so we do a lot of sculpting as we're doing that pattern transfer. And there's a lot of research that goes into how to do that.
Yeah, so there is a sort of a design problem as well as a manufacturing problem, just like the chip design and manufacturing issue, right?
Exactly.
Yeah. Do you see at that scale, Randy, do you get into quantum effects like quantum tunneling and stuff like that? Or?
No, we don't have to worry about that. Everything behaves well, or Newtonian, you could say. The size scale of feature that we're looking at is much larger than the atom, the atomic scale on the silicon. So we don't have to worry about that.
Okay. So Randy, we'll take a quick break. When we come back, we'll talk about your recent paper in the ultraviolet and soft X-ray diffraction
Sounds
area.
Good.
This is a Scientific Sense podcast providing unscripted conversations with leading academics and researchers on a variety of topics. If you'd like to sponsor this podcast, please reach out to info@scientificsense.com.
So Randy, we are back. We were talking about the design and manufacturing of the large format X-ray reflection grating, gratings that you fly in the suborbital missions that is quick and less expensive, but can take large payloads, at least from a testing and experimental perspective before you actually send it up in very costly missions, orbital missions. These gratings are as intricate as a silicon chip to design and manufacture. You have another paper, Extreme Ultraviolet and Soft X-ray Diffraction Efficiency of a blazed reflection grating fabricated by thermally activated selective topography equilibration. So what is thermally activated selective topography equilibration?
Yes, and so as you probably saw while you're reading that taste, and so I'll call it taste.
Yeah, right.
And so what that allows us, if you remember earlier, I mentioned that we do a lot of work in the controlling the topology of the features that we make for our X-ray gratings. And so not only do we draw these intricate patterns, but the way that we transfer them and create structures to our what we call our X-ray grooves, we like to investigate different ways of doing that. And so by default, if I were just to make a binary pattern where there either was structure or there wasn't structure, and I wanted to transfer that into the silicon, you might imagine that that would make structures that look rectangular, where you either transfer it or you don't. And so it would make these rectangular grooves. But if there's ways of making other structures, trapezoids, triangles, especially triangles, then you can add an additional amount of control into where you put the photons in the spectrum. And so this process is called blazing the grooves. And so when we put this blazed profile or this triangular profile on the grooves, we direct more light orthogonal to that facet. And so in other words, when X-rays shine onto this grating, instead of making a spectrum that goes everywhere, that spectrum only goes to a specific position. And this is important because that allows you to A, accentuate an important part of the spectrum where most of the science is located, but also B, create a lot of efficiency where most of the light is going to that position. And in that position, you're getting high resolution as well. And so our ability to scope these grooves is important. Now, taste comes in because what taste does is that the electrons from the electron lithography tool we're varying the amount of electrons that are hitting the resist. And what that does is it varies how much you expose the resist, which varies how much is developed away during that development step. And so you can actually put a relief or some structure into this resist. And if you want to influence that structure even further, that resist will flow or start behaving not as much of a solid, but more like a liquid as you increase the temperature. And so taste then takes a thermal cycle to the resist afterwards and causes it to flow and create a more triangular profile after we've done that electron manipulation. And so it's a way it's another different way of getting a triangular profile.
Do we use these techniques in chip design today, or do they have some applications there too?
To be honest with you, I'm not sure. I don't know what the applications of this are on a wider scale.
Okay. So again, going to the 2018 mission, you had an objective of the supernova remnant. So do you have some sort of ex-ante expectation of what that spectrum might look like, and you're designing for it, or you don't really know?
We do have some expectation because other parts of the remnant have been observed before by other X-ray missions like the Chandra X-ray Observatory or XMM Newton or ROSAT, which was a older mission. These X-ray observatories have observed Vela supernova remnant in various fields of view. The area that we were looking at was an area that was not observed very much. It was only observed by the ROSAT observatory, and that observatory doesn't have very good, doesn't create very good spectra, and so you get nice pictures and you get a little bit of idea of what the emission looks like, but you don't have a really good idea of what the spectrum looks like. And so we're looking at this kind of area that has very little spectral knowledge of it. So based off of the rest of the remnant that had some spectral knowledge of it, we can give a guess at what this plasma would look like, but you wouldn't be sure until we actually observed it.
So in some sense, you are trying to confirm something, right? So is it possible to look at something that you have no idea about and get some data from it also?
Yes, it is. I think that when it comes to interactions in the universe, there's a lot of different categories of them. But in general, those interactions will produce certain wavelengths, a certain spectrum. And so if you're concentrating on a certain interaction, say in this case, a supernova explosion, and its shock wave as it hits the interstellar medium around that star, that dying star, that you can be pretty sure that interaction is going to give us X-rays, and that those X-rays will create a spectrum. Now, so if you observe something like that and you have no idea what the spectrum looks like, it just so happens that in the energy regime that we work in, which is the soft X-rays, the abundant elements of our universe, take a look at the first, 26 elements of the periodic table.
Yeah.
Those elements have, at those temperatures, have most of their electronic transitions in the soft X-ray. So we know that we're going to see photons there. And so it's just a matter of observing them and finding out what they tell us.
Yeah, I mean, the manufacturing of this is really complex. The paper says as the structure was coated with 50 nanometer of gold by electron beam physical vapor deposition using titanium as an adhesion layer and then tested. So these are done by NASA, or you do it in the university?
Yeah, we do all of it here at Penn State, and Penn State has a fantastic facility, the Nanofabrication Lab and the Materials Research Institute. It's incredible both because it has a wide range of high quality tools which allow us to do all of this processing, and also high quality staff that's available to help out with the processing and to help out develop the necessary recipes. And so it's a great space to be able to do this research and get to the point where you're producing high quality instrumentation.
Yeah, but it's really exciting. It seems like it's sitting at the intersection of astrophysics, fundamental physics, material sciences, and other areas. So it is really sort of a multidisciplinary focus here, right, to make something like this.
It definitely is, and but I think that's what keeps us on our toes. It means that we have to be sure that we know what we're doing in several of these areas, but also opens up lots of opportunities. There's fields of optics and photonics that we work in as well, because that's part of what we do, but it's also interesting. And like you said, there's parts, some material science projects that we're interested in as well. So it has a lot of offshoots.
Yeah, it's exciting research. Randy, so in conclusion, when you look forward, what is one or two areas where you think we could make a significant improvement, let's say next 5 years?
Yeah, and so we're always looking for higher throughput and higher resolving power. And the last part I haven't talked about much, but that's really how small can you get a spectral line? And the smaller you can get it, the more information you can get out of a spectrum. And so, at least for us, we strive to really beat down those performance metrics so that we can get increased performance. And because of that, there are missions that are on the horizon. I'd like to mention the Lynx mission, which is a large flagship NASA mission that's currently being considered under the Decadal survey. The National Academy of Sciences does every 10 years does a survey of astronomy and astrophysics to say, what are the key projects that we want to move forward? What is the key science we're trying to find? And Lynx is one of these missions that's one of these, billion-dollar class missions that's trying to be a large flagship mission in the future. And, a lot of what we do is trying to work towards enabling the goals of that and enabling Lynx to be able to do the science it wants to do. And so creating not just these gratings, but the detectors and the optics and just, knocking down the challenges that are presented in front of us so that we can actually make large steps towards these large goals to make this fantastic new observatory. So that's really what it's all about.
Yeah, and it is X-ray and ultraviolet. So these are areas of the spectrum that we don't really have at least comparable information compared to visible light, right?
Oh, yeah, indeed, for sure. I mean, for visible, you can do a lot of work from the ground and build large telescopes on the ground, which is kind of what's happening now and in the next decade. And so for the UV and X-ray to keep up, we need additional throughput in space.
Right. Excellent. Yeah, this has been great, Randy. Thanks so much for spending time with me.
Of course. Thank you so much for having me. It's been fun.
Absolutely. Thank you.
This is a Scientific Sense podcast providing unscripted conversations with leading academics and researchers on a variety of topics. If you'd like to sponsor this podcast, please reach out to info@scientificsense.com.